Okay, in this mini lecture, we're going to talk about how to project the flux or the gradient of your FE solution for plotting or other analysis. So towards the beginning of the semester, we talked about the different steps of a finite element method. We have pre-processing, then we assemble a global system. That means assembling your stiffness matrix or your conductivity matrix, applying boundary conditions, solving the system of equation, and now post-processing. So, for example, if we take a heat transfer problem, then the solution of the heat transfer problem, T sub x, we know that it's interpolated from our shape functions, which are C0 continuous, and so we can just directly plot this using the patch command in Matlab. So this is just like what we did in the demo, where you had a patch. Here it's a little different. Instead of creating a patch object, this is the other way you can call the patch command. You call it with a bunch of arguments, so you basically will first call it with an argument of a string that is vertices, and then pass in the nodal coordinates. Again, you have to transpose it just like you did when you created the structure. Then faces, and then you pass in the connectivity matrix, and that's actually a mistake. That should be a transpose, just like it was before. Then we're going to say we want to interpolate the face color, so it's face color interp, and finally face vertex C data. And now we're going to pass in D, which is our nodal solution. So that's the solution from KD is equal to F. However, if we wanted to plot the heat fluxes, now this is a little trickier because the heat fluxes are the gradient of the temperature field. The temperature field is C0, and so therefore the heat fluxes are C-1 or discontinuous functions. And what this means is that if I were to look at a single node, then I'm going to get 4 different values of heat flux. And the reason I get 4 different values is because if I evaluated the heat flux using the nodal variables from either of those 4 elements connected to that node, I would get 4 different values of flux. And so to nicely plot the heat flux, what we want to do is something called a least squares projection. And the basic idea is this. So we would like to have a continuous heat flux, which we'll call Q tilde. So that's a continuous heat flux field. The way that it's written now, it's a vector field, so it has 2 components, and it's a function of x, which is a vector, or the position. And that's going to be equal to our shape functions times some nodal values of Q. So we're going to interpolate the heat flux just like we interpolate the temperature. Now, of course, what we need then is we need to be able to calculate Q sub I. We need to be able to calculate the nodal heat flux values. And to do that, we're going to cast it as a minimization problem. So in other words, what we'll do is we'll take Q sub x, which is our finite element heat flux. This is C-1, so that's what we want to represent as a smooth field. And we're going to subtract from that Q tilde, or NiQi. And so what we're looking for is the Qi that makes NiQi as close as possible to the FE solution as possible, except that of course it'll be continuous. And so to do that, what we'll do is we'll square that difference, and then integrate it over the domain, and then we want to minimize that for the Qi. So how do we do that? So to minimize a function, you usually take a derivative and set it equal to 0. And so what we're going to do here is we're going to take a derivative with respect to Qj. So we're taking a derivative with respect to each of the nodal heat fluxes. It has to be Qj and not Qi because we already have 2 i's, so this has to be a new index. Another way to think of it is this is a function which is a variable of lots of q's, all the different qi's 1 through n, and this is going to set up a system of equations, n systems for n nodes, and so we need each of these derivatives with respect to qj is going to be an equation that we set to equal to 0. The solution to that system gives us the qi that is going to represent our heat flux field. And so to take this derivative, it's not very complicated, even though you may not have seen something like this. So we take the derivative, goes right inside the integral, there's no problem there. When it hits the square term, the derivative of squared term here becomes twice the term itself, so just the same thing as the derivative of x squared with respect to x is 2x. So here's 2 times the term, and then we have to take the derivative of the term. So the derivative of the function q sub x, that's our FE function with respect to qj, is 0. They don't depend on each other. And so what we have is the derivative of ni qi, and so what we'll have is that's written here with the negative sign carrying through. Now we can't repeat I again because we have the rules of index notation is you can only repeat a variable twice. So now we're just going to switch qi to k. So I becomes k, so it becomes nkqk. This is just a sum. And so the 2 terms that we need to know is the derivative of nk with respect to qj is 0, because the shape functions don't depend on whatever nodal heat flux values we have. And then the derivative of qk with respect to qj, well, if I is not equal to j, then they don't depend on each other, and otherwise they're the same thing. So this just becomes delta kj, or the Kronecker delta. And so plugging that in, we get that the difference of q sub x minus ni qi, that was the first term, times the derivative of that term, which is going to now be nk delta kj, that integrated over the domain is equal to 0. And so whenever you have something like nk delta kj, all that does is it's a swap. So it basically says I'm going to replace index k with index j. So this just becomes nj. So rearranging this expression, if I distribute that nk out, or it's nj out and switch variables, then what I'm going to get is, oops, sorry about that. What I'm going to get is that I have the product of ni and j. That's what we call the tensor product. So that's going to create a matrix from vectors. That integrated over the domain, we can pull qi out because it doesn't depend on space. That is going to be equal to the integral of nj times q of x. This is of course, my FEA solution, heat flux, integrated over the domain. And so we can rename this integral of ni and j, just call it some matrix aij. The whole right-hand side we can evaluate shape functions and finite element solutions. This is post-processing, so of course we already know we're already able to compute the FEA solution. And so what we get out of this is we get that, let's write it this way, so we get aij times qi is equal to yj. And then because you can see that a should be symmetric, because if I switch I and j, the shape functions are ni and j, or nj and I would be the same thing. And so what I get out of this is I get that qi, my nodal heat fluxes that are projected to the nodes, is just equal to the inverse of this A matrix times the right-hand side y. And so let's just quickly talk about how to implement this in code. So we're going to do an integral over the whole domain, and we'll integrate both y and a in the same loop. A is going to be sparse because it's product of shape functions, and so it'll have roughly the same sparseness pattern as our stiffness matrix did. And so we'll allocate it as an n by n matrix, and in a mesh where we have 4 node quadra elements, then each node is associated with 8 other nodes, or 9 including itself. So each row of the stiffness matrix will have 9 non-zero values, less on the ones on the boundary, but 9 is a good estimate just for the sparse matrix. The right-hand side y is going to be an n by 2. Now the reason it's by 2 is because the heat flux has 2 components in 2D. So if we solve the 3D problem, it would be n by 3. Then the procedure is going to look very familiar. So we're going to loop, here we are here, we're going to loop over the connectivity matrix, which is going to give us the nodes of each element. We're going to gather our element nodal coordinates, just as we've always done. We're going to gather our solution, and I'm just pointing out here, I'm transposing the solution, the gathered solution, just so that the nodal coordinates and the solution, the element solution variables have the same format. They should both be the number of components. In the case of the nodal coordinates, it's 2 by 4, and the solution is 1 by 4, so it's the number of components by the number of nodes in the element. So in both cases, XE and DE would have 4 columns. Then what we're going to do, just like before, we don't want to scatter to a sparse matrix within our quadrature loop because it's a little bit inefficient. So we'll create a element A matrix. So this is just going to be like that n transpose n term, and it's just going to be a 4 by 4, or we could do length of C to get the number of nodes in the element. So that's nothing new. And then we're going to loop over our quadrature points. Here, the quadrature points you're going to define, you could either define it as a just typical 2 by 2 quadrature. For this class, that's fine. It might turn out that you want to use fewer quadrature points if you want to make this post-processing cheaper, but 2 by 2 is fine. Then you're going to do the regular thing. So you're going to evaluate your shape functions and their derivatives. You're going to evaluate the Jacobian in the usual way. You're going to then transform the derivative of the shape functions with respect to parent coordinates to the derivative of the shape functions with respect to global coordinates by multiplying by J inverse, or in Matlab, dividing by J. Then this might be a little new. When you compute the heat flux, it's just Q is equal to minus the conductivity, K, which is a material constant you would have had to define, times your nodal unknowns, or your nodal temperatures. They're not really unknowns at this point, you've already solved for them, times dn dx, the derivative of shape functions. And just to review, dE was 1 by 4, dn dx is 4 by 2, and actually this is a mistake in the notes, and so this is going to end up being a 1 by 2 is Q. Then what we're going to do is scatter this to our element matrices, or compute the element matrix first. So AE is just AE, so zeroed out before the quadrature loop, plus n times n transpose plus the determinant of J times the quadrature weight. Again, the way that we typically evaluate the shape functions is that they're already transposed, so n transpose n becomes nn transpose. But what's important to note here, you have to make sure that this term evaluates to a 4 by 4 and not to a 1 by 1, because if you get it backwards, it'll be a 1 by 1. And everything will work, but you'll get weird answers because you'll add just essentially a scalar value here to a 4 by 4, and it'll add the scalar to all 4 values. So make sure that when you do this, double check to make sure that n times n transpose actually makes a 4 by 4. Then we'll scatter the right-hand side, so now it's y sub c, and then colon, that's for the 2 components, is equal to itself, plus n times q times determinant of j times q end. And again, I want to point out that n times q is going to be 4 by 1 times 1 by 2, so that makes a 4 by 2, and that's getting scattered into y sub c. C has 4 values, and so this y sub c comma colon is also a 4 by 2, so the dimensionality works. We'll jump or end out of the quadrature loop, and then the last thing to do is to scatter the element A matrix into the global A matrix. Then we end, this end corresponds to the, let's see if I can fit it here, corresponds to the looping over the number of elements, or looping over the connectivity matrix, and that then completes our evaluation of A and Y. And so finally, the nodal fluxes is just A inverse times Y, or more efficiently, A backslash Y. Now, this approach can also be used when we get to it to compute any time we want to evaluate the gradient or a solution that depends on the gradient of our finite element solution, we can use it. So you could use it to compute the continuous stress or strain fields when we get to elasticity problems. You can do more advanced things, like if you wanted to compute something like strain energy density, which depends on the stress and the strain, you could project. So basically, whatever you compute in this box here is going to be what you're going to project to a continuous C0 field. And so that's it for now. We'll do one more short lecture to talk about the method of manufactured solutions.